Well, hello math fans, Mr. Gibson here today to talk to you about lesson 3 in our unit on permutations and combinations. So, aptly titled, Permutations Involving Identical Objects. Well, what do we mean by identical objects? This is a silly question to ask, yet let's go with it anyway. If we take a look at the letter E, and we draw another E, but this time we make it a different color. Let's say this pretty forest green here. It's pretty obvious to tell the difference between the E's. So if we start playing around with what order they're in, we'll know where the green E is versus where the red E is. But what if we switch this up a bit? What if instead of a green E, we draw another perfectly identical, even though my writing sucks, red E? All of a sudden, we can't tell which one is which. There's no distinguishable mark to tell us the difference between the two. So we're going to have some overlapping permutations when we start to come up with all of our different possibilities. Meaning that if we use the typical math that we've been using, we're going to end up with more permutations than what we actually have. So we're going to have to figure out how to deal with that. Well, let's take a look at example 1 here. Now, I want to point out one major thing here. We've written at the top here this idea of investigate. And what we were hoping, and what I hope, is that you go ahead and you work through this by yourself. This is a very student-led type of lesson that if you go through the questions and really put those brains to work, you should be able to come up with all of these solutions on your own. However, I'm still going to go through the process of explaining each of the particular examples, but I'm really hoping that you pause this now, take maybe 20 minutes, work through some things, and see what you got. Okay? But for those of you that don't care to do such a thing, let's just move along. Let's start with this particular question 1 here. The permutations of 4 different letters, A, B, E, and F. Well, these are all distinct letters. We definitely know what an A looks like from a B, from an E, from an F. Meaning when we go to write out all of the possible permutations, and we've done that for you to save you a little legwork, we end up with a beautiful number of 24. Now there's a couple of mathematical ways we've found to do this instead of just doing the brute force method. One of them is the fundamental counting principle, meaning for the first letter we had 4 possibilities. For the second letter then we only had 3 possibilities. For the third letter we had 2 possibilities, and for the last we only had 1. Which is equal to 24. Remember, you just have to multiply the numbers together. We've also come up with a different notation to describe this, and that's this idea of factorial, meaning that 4 factorial is also equal to 24, and these particular expressions are equivalent to each other. So, we've shown in 3 different fashions that we definitely get 24 permutations if all of our objects are distinguishable. Now, let's throw a monkey wrench into this idea. And let's change all of those F's into E's. So now, in example 2, we are going to have the letters A, B, E, and then another E. And we have to come up with all the different permutations for this. Well, what happens here? Well, instead of all these F's that we have down here, now we are going to have E's. And if I change all these F's into E's very quickly, what you should start to notice is we start to get some repeats. Well, that's not cool because repeats just means that the same thing has happened more than once, and we don't want to count that in our final count. We want to know the number of different permutations we have, not any repeating permutations. So, well, let's take a look. If we take a look at the first column here, the second column are all just repeats of the first column, which means we don't want to count those anymore. Those are the same thing. That means our count is an overestimate. If we take a look at the third column now, it's the same thing. All of these objects are just repeats of column 3, so those don't count. And wouldn't you know it, in column 5, it's exactly the same thing. They're all identical to each other, so we don't count those. So the number of permutations when we have 2 identical objects actually gave us an answer of 12 total permutations. Well, if we compare this now with exercise 1, which is what our next question involves, we can see very simply that we started off with 24 permutations at the beginning, and then we ended up with 12 permutations when we had 2 identical objects, which means that the number in question 2 is 1/2 of 24, or 24 over 2. Now, if we were to write this in factorial notation, we can rewrite this as, well, 24 is just 4 factorial over 2 factorial. Well, this is an interesting result, because if you take a look, 4 factorial is just the number of total permutations that we had from our initial question, and 2 factorial are the number of ways that e's can actually be rearranged, because there's 2 objects and they can be arranged 2 factorial ways. Well, isn't that cool? I wonder if that follows through into a different situation like this. Hint, hint. So let's take a look at question 3. Now all of a sudden we have, okay, screw having 2 similar letters. Let's go ahead and have 3 similar letters. And in this case, we're going to have nothing but B's and A's, but we're going to have 3 B's and we're going to have 1 A. So if we take a look at our original list, all of a sudden all the F's and E's become B's. Well, this ends up being a very interesting situation here, because now if you take a look at the first row, every single entry is an A, B, 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 which means that one doesn't count, that one doesn't count, that one doesn't count, that one doesn't count, and that one doesn't count. And I think if you take a look now, what you'll also notice is that when we do row number 2, oh my, they're all the same yet again, meaning that all the entries in row 2, except for the first one, cancel out 2. And this pattern continues through the remaining 2 rows, where if we change the E's and F's to B's, all of a sudden all the other entries cancel. Which means that when we have 3 identical objects, we actually end up with 4 permutations. Well, let's compare that now to exercise 1 again. Well, we started with 24, we ended up with 4, which means we actually ended up with a 1/6 of 24. Or if you wish, we could write it as 24 over 6. Or if we write it in factorial notation, that's 4 factorial over 3 factorial. But wait a second, 4 factorial is just the number of permutations we started with in question 1, and 3 factorial, that's not a 31, that's a 3 factorial, is just the number of ways that we can arrange these 3 B's. Well, that's wicked. I wonder if this works in all cases. And let's take a look at part A. The first thing you should always do is count the number of objects you have, and then count the number of identical objects you have. So let's start with the obvious. We have 1, 2, 3, 4, 5 objects. And of those 5 objects, we have 1, 2 that are repeated or identical. Well, if you take a look at our previous questions, the way we came up with our solutions using factorial notation was we took the number of objects, which was 5 factorial, took all the possible combinations of them, and then divided it by the number of combinations involved in the identical objects. And in this case, that means there was 2 identical objects of D's, giving us a final solution of 60 permutations. Well, let's extend that to part B. Now again, we started with our 5 factorial. Well, that's not it. All right, let's extend that to part B now, where instead of 2 identical objects, we actually have 3 identical objects in a set of 5 objects. So again, the total number of permutations for 5 objects is 5 factorial, divided by the number of permutations for 3 objects, which is 3 factorial. Remember, that's just directly relating to the number of identical objects that we have. And we end up with a number of 20. C then, if we follow the exact same pattern, there was 5 objects to start with, and of those 5 objects, 4 of them are identical objects, giving us a beautiful number of 5. So, if we take a look at the general case, the numerator involves the number of ways that you can permute 5 distinct objects, and the denominator represents the number of ways you can permute the identical objects. Well, how are D and E going to work then? Well, since we now have 2 sets of identical objects, and I'm going to do these in the worst possible colors, we still end up with 5 objects. So the permutations of 5 objects is 5 factorial, but now we have to deal with both sets of repeating objects. So in this case, there's 2 factorial ways of dealing with the B's, and there's 2 factorial ways of dealing with the C's. And if we equal that out, the answer we get is 30. So now all of a sudden we had 2 different sets, and each set had to be dealt with individually, but you still multiply those particular ones together. Counting principle. Let's take a look at E. And since I ran out of space, I'm going to do this like that. And we end up with, well, we still have 5 factorial for the permutations of 5 objects, but now we have 2 sets of identical objects. One of them, there are 3 factorial ways of permuting them. And in the other one, there are 2 factorial ways of permuting them. Do you know which one's which? Should be straightforward now. 3 deals with the 3 A's and 2 deals with the 2 B's. That's a whole bunch of arrows. Let's get rid of this one here. Apparently, we'll get rid of all of them. And what do we end up with? We end up with the number 10. So, tricks to this, you count the number of objects, that's your numerator. You count the number of identical objects. If there are multiple sets of identical objects, you have to deal with each one individually. But what we end up with is this beautiful generalization, which tells us that the number of permutations of n objects, of which there are A objects alike of one kind, B alike of another kind, and so on and so forth, you can use this equation right here to count the number of permutations. And that really is just what we've been doing if you take a look at our previous examples. So, if you got to this point by yourself, congratulations, you are a math wizard. And if you did not, don't panic, because I'm going to give you plenty more opportunities to deal with that now. So, you have an equation. This should be rather straightforward. If we take a look at the number of permutations for all the letters of the following words, all you need to do, count the number of objects. In this case, there's 4 objects. Count the number of repeating objects or identical objects. And there's 1 set of O's, and there's 2 of them. So there's 2 factorial ways of arranging them, giving us a total of 12 permutations. Mississippi, a word that I am so glad I still know how to spell, has 11 objects. There are 11 letters in the word Mississippi. So there's 11 factorial. Now, we have to find all the repeating letters, and we know there's a bunch. So if we take a look at S's, there are 4 S's. So that means there's 4 factorial ways of arranging them. If we look at I's, there's 1, 2, 3, 4 I's. So 4 factorial ways of arranging those. And if we take a look for the p's, there are 2 p's there, so there's 2 factorial ways of arranging those. If you equate all these together, what you should end up with is 34,650 permutations. Bigger number, but a lot more letters. Just imagine again throwing all these letters together and jumbling them around, but because we can't tell the difference between the S's, some of them are going to repeat themselves. Let's take a look at Ogopogo. Hey, I'm from Kelowna. Go figure. That's cool. Let's take a look at, well, there are 7 different objects. And let's take a look at repeating letters. Well, we have O's, and there's 1, 2, 3, 4 O's, so there's 4 factorial ways of arranging those. And we also have G's, and there's 2 G's, so 2 factorial ways of arranging those, giving us a beautiful number of 105 permutations. Statistician, I won't belabor this any more than I have to. We see that there's 12 objects. Count up the different repeating letters. There's 2 S's, and there's 3 T's, and there are 2 A's, and there are 3 I's. And if you take all that into account, you're going to end up with a whopping number of 3,326,400. And voila! We are done. You're going to see a bunch of different ways of wording questions like this, but my strategy to you is always write these out as a set of letters. If you write it out as a set of letters, you're not going to be confused with how do you deal with the identical colors or letters or whatever. So let's take a look. How many different ways can 3 red balls, 4 blue balls, and 2 yellow balls be arranged in a line? Well, let's just write it out in letters. We have 3 red balls. We have 4 blue balls. And we have 2 yellow balls. Hope that yellow pops up on your screen. So, from here, it's just a simple plug and chug. We know the equation. Let's use it. We have 4, 5, 6, 7, 8, 9 different objects. So 9 factorial ways of arranging those. And now we just go through. There are 3 reds, which means there's 3 factorial ways. There are 4 blues, so 4 factorial ways. And 2 yellows, so 2 factorial ways, which all equates to 1,260 permutations. See the power now in writing these out as letters? Makes life simple. What about question 3 now? A coin is flipped 6 times, and how many ways can you get 4 heads and 2 tails? So in this example, we're looking for a particular set of results. And what we're saying is we want 4 of them to be heads, so I would write those out as pretty green H's. And 2 of them tails, let's write those out as orange T's. Well, it's a bunch of letters. We're just trying to organize them. 6 total objects, so 6 factorial ways of arranging them. We have 2 sets of identical objects. One of them has 4, so there's 4 factorial ways, and the other has 2, so there's 2 factorial ways, giving us a total of 15 permutations. It's just that simple, ladies and gentlemen. We'll keep rolling along. We'll get to the hard ones here in a second, but let's do one more. Question 4 says that a true-false test has 7 questions. How many answer keys are possible if 3 answers are true and 4 answers are false? Be careful now not to do your gut instinct, which could be just, I want to know how many answer keys there possibly are. We have a very specific number we're looking for, and that's in the idea that we have 3 answers that are true and 4 answers that are false. So remember that if we were just looking for all the possible answer keys, well, that would just be, again, counting principle. There's 2 possibilities for the first, 2 for the second, 2 for the third, which just multiplies the other to the 7th, which would equal 128 possible answer keys. However, that's not what we're looking for. We're looking for the case where we have 7 objects, so 7 factorial ways of arranging them. And of those particular objects, we have 2 sets of identical objects, 3 in the first set, 4 in the second set, giving us a total of 35 possible answer keys. So the wording may be a little different, but the question is just asking for the same thing. If you have indistinguishable objects, this is how we deal with it. Question 5 is a very typical permutations with identical objects type problem. It asks that on the following grids, if we start at point A and we want to get to point B, how many different paths can we take to get there? Well, if we take a look at grid A here, something interesting to note is that if we pick, let's just pick 3 random different paths. And the first one I'll pick will be straight across and down. Second path will be, let's make it different. Let's go down and over and down and over and down and over. And let's pick a third path as well. Let's go over, down, over, over. Sure, why not? And like that. So we have 3 distinct paths. Now, the question made it very clear that we can only travel east and south. So you can't go backwards, you can't go up, you have to go to the right, and you have to go down, and that's the only way you can do it. And I promise you that all questions of this type, almost every single one will involve a very direction-based sort of way to go. So you won't ever have to deal with the situation that you're going backwards. So if we take a look at these 3 paths, something interesting occurs, that no matter which way we traveled, we still traveled 1, 2, 3, 4, 5, 6 blocks to the east, right? There's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it was always 6 blocks east. So let's write that out as letters. And no matter which path we took, we always went down 1, 2, 3, 1, 2, 3, 2, 3. Always went south 3 times. So if we write that out as letters, we get this particular set. Well, this is cool because we've dealt with situations like this where we have a set of 9 objects where we have 2 sets of identical objects of different values. So what do we do with that? Well, count up the objects. We have 9 total objects, so there's 9 factorial ways of permuting them. And now we deal with the identical objects. There are 6 factorial ways of arranging the E's, and there are 3 factorial ways of arranging the S's, which means we end up with a total number of paths of 84. So again, as I mentioned previously, there is great power in writing these out as letters. It's a whole lot simpler to deal with a string of letters instead of actually drawing out all the paths. And I would love you to draw out 84 paths, but we don't have that kind of time. So B and C are slightly different. C is definitely different because it is a 3-dimensional object. But for B, this one's different because it doesn't matter what happens, you have to go through this choke point here. So if we think about this in terms of the total number of paths, well, we're going to have 2 situations here. We're going to have situation number 1. We'll call this P. And situation number 1 says, well, how many different ways can we get from A to P? Well, using the logic we just used, we go east 3 times and south twice, which means we have 5 factorial ways of arranging 5 objects. And then we deal with our identical objects. 3 factorial for the E's and 2 factorial for the S's. And that gives us 10 different paths. But that only got us to P. So second situation now is how do we get from P to B? Well, we have to go east 3 times and we have to go south 3 times. Meaning now we have 6 objects, 6 factorial, over 2 sets of identical objects, each with 3, giving us a total number of paths of 20. Well, back to the fundamental counting principle. We have two different situations to deal with. Multiply them together. The total has to be 10 for the first path to get to P, and then times 20 to get from P to B, giving us a total of 200 permutations for this situation. So we had to break it up into 2 steps, and once we broke it up into 2 steps, the mathematics was relatively straightforward, provided you understood that at the end, you're basically just counting by multiplying. All right, part C, again, it's getting a little redundant at this point, but in our case now, we have 3 directions to go. We have east to travel, we have south to travel, but we also have this direction. Let's call it forward. So we're going to have 2 paths to the east. We're going to have one that goes south, and we're going to have one that goes forward. Well, that's just equal to, we have 4 objects, and of those we only have 1 repeating set, and there's 2 factorial ways of dealing with those, giving us a total of 12 permutations. So, even with a 3D object, again, if you can only go east and south, you have to move forward at one point, and there's distinguishable objects, so we don't have to deal with any repetitions that way. Question 6 is really just an extension of the rule we've been using. We have to kind of play with the words that we're using a bit. So let's take a look. How many different 5-digit numbers can you make using the digits 1, 2, 3, 4, and 5 if the odd digits are in descending order? Well, if we write that out, what we really want is that 5, 3, and 1 are in that order at all time. And after that, we're going to have whatever. Well, if you think about 5, 3, and 1 as an absolute, that we don't want to switch these around, well, that's really saying the same thing as if they were actually identical objects and we were trying to remove the repeats. Yes, these are distinguishable objects, but if we treat them as identical objects, then we remove any sort of flip-flopping that we do with these values. Meaning, we can just write this as we have 5 objects, and we're dividing by our set of 3 identical objects, quote-unquote, factorial. And that's going to give us an answer of 20. So again, all we're saying is that if we don't want them to move, but they're going to probably shift from like the 2nd spot to the 4th spot or to the 5th spot, we're trying to eliminate any sort of permutations of those 3 numbers that we have to begin with. Thinking in the same lines, if the even digits are in ascending order, we know that we want to have it as 2 and 4, and then we can have whatever after the fact. Well, it's just the same idea. We have 5 factorial for number of permutations of 5 objects, but in this case, if we treat them as identical objects and we want to eliminate all the possibilities of moving those around, there are 2 factorial ways of rearranging those, giving us a total value of 60 permutations. So, a bit different way of thinking about those. However, again, really try to understand this idea that if we think of them as identical objects, then we're eliminating any sort of permutations that we have to deal with those 3 objects. Okay? So, question 7 says, well, the letters of the word barrier are arranged in the following ways. Find the number of arrangements possible. The simple and most effective way of dealing with this is draw yourself your boxes showing the 7 possible locations of letters in the word barrier. Okay, so we have our boxes here, and question 1 says, or A says, words that begin with R. So in that case, we have an R that absolutely has to go there. Which means, what are we left with? Well, we are left with B-A-R-R-I-E. That's it. Because the other R there we dealt with as the first letter. So, well, let's take a look. We have a total of 6 objects now. So 6 factorial ways of dealing with it. And of those objects, we have one identical set of 2 objects. So 2 factorial to divide by, and we end up with 360 permutations. So again, exactly what we dealt with before. But of course, once we dealt with this r, there's only one way to arrange that r. So really, it's 1 times 6 factorial over 2 factorial. If we deal with b now, words that begin with 2 r's. Well, if we put another r in here, there's still only one way we can arrange that. We eliminate one of our possibilities here, and apparently my eraser is huge. What are we left with? Well, in this case now, we have 5 factorial objects, and none of them are identical. So the answer now is just 5 factorial ways of permuting them, giving us an answer of 120 permutations. And on to C, begins with 3 r's. Well, I think you're starting to see a pattern here. If we eliminate that other r, all we have left is 4 objects. There's 4 factorial ways of arranging those, giving us an answer of 24 permutations. So, first 3 are fine and fairly straightforward. The last 2 are a little trickier. Words that begin with exactly 1 r. This word exactly should just raise red flags at you, because what it means by exactly 1 r means that it can't be an r after the first r. So if we draw out our boxes again, I'll do it in different colors just to be cool. We have still 7 objects to deal with, and we have an r in the first box. However, we can't have an r in the second box. So if we take a look, B-A-R-R-I-E, if we can't have an r in that second box, there's only 4 other objects that can go in there. So there's really only 4 choices to choose from there. From there, though, look what we have. We end up with 5 objects, and of those 5 objects, 2 of them are identical. So this particular section means there's 5 objects, and there's 2 identical objects, so we have to deal with 2 factorial. And multiplying everything together, if there was a possibility of 1 for the r, 4 for the second, and then 5 factorial over 2 factorial for the rest, this all goes together to give you 4 times 5 factorial over 2 factorial, which equals 240 permutations. So again, there was only 4 possibilities for the second one. This is just fundamental counting principle for the first 2 objects, but after that, now we can deal with our equation for permutations, deal with the last 5. Looking at E now, hopefully this makes a lot more sense. E, instead of having a possibility of 4 in the second box, now we're saying, well, we just want an r in there too, and there's only one way that we can arrange an r, or one object to choose from that way. And in the third box, well, if we get rid of the r, we can't have an r in the third because it says we have to have exactly 2 r's. Means there's only 4 objects to choose from in the third box, meaning that the remaining permutations that we have to choose from is just 1 r, 1 I, 1 e, and 1 either b or a, or whatever. 4 factorial ways of arranging those. We've run out of identical objects, meaning that words that begin with exactly 2 r's is just 1 times 4 times 4 factorial, which is just equal to 96 permutations. And again, just a reminder, this was 240. by all that fancy math. Okay, so drawing boxes, visualizing where those R's are going, where your letters are going, that's a big deal. Question 8, I am going to go through with you with the understanding that you probably pushed pause and worked on it yourself. I can expect this to be a test question. I love this question because it's got that little extra trick in it that you really need to pay attention to. A language teacher wants to keep books on the same language together on the shelf. So we have these different languages here, but they want to keep the exact languages together. If there are 12 spaces for 5 different Ukrainian, 4 different English, 3 different French books, how many different ways can they be placed on the shelf? Well, if we just deal with the languages individually, if we call this purple Ukrainian, there's definitely 5 different objects because, again, it says different. Different means that they are all different books. They are distinguishable. So there's 5 factorial ways of arranging those. And if we take a look at our English books, and we'll make those red, there are 4 factorial ways of arranging those. And if we take a look at our French books, there are 3 factorial ways of arranging those. So the initial answer then would be the number of permutations is 5 factorial times 4 factorial times 3 factorial. However, we have negated one important feature here, and that's the idea that we have Ukrainian books, English books, and French books. And within each of those boxes there's a number of books. We still have different ways that we can arrange the languages themselves, which means there are 3 factorial ways of arranging these languages, meaning that included within our particular list is also this idea that there's 3 factorial ways of arranging the languages, and all of these different ways of arranging each book within the language, giving us a total number of permutations of a whopping 103,680.